arc length method is a substitute for automatic time stepping, with some additional, displacement-based solution controls. It selects appropriate load increments to facilitate a faster convergence with a stable solution. Consider a load deformation curve of a system, shown in the figure. Let F applied be the total load applied on the structure. Let F1 be a part of the load applied in the first substep. Let K1 be the initial stiffness of the structure. Let delta 1 be the initial deformation in the structure, assuming applied load F1 and the initial stiffness K1. From the figure, we can calculate arc radius R1 as R1 square is equal to F1 square plus delta 1 square. However, we know that the applied force F1 is equal to K1 multiplied by delta 1. Substituting the value of F1 in the above equation, we get R1 square equal to delta 1 square multiplied by K1 square plus delta 1 square. We can take delta 1 as a common factor and write the equation as R1 square equal to delta 1 square multiplied by the bracket K1 square plus 1. From the equation, we can conclude that if K1 tends to 0, R1 tends to delta 1. Thus, arc length R1 represents a radius of the circle, representing all the possible combinations of F1 and delta 1 for various different values of stiffness K1. If the stiffness K1 tends to infinity, the deformation delta tends to 0. Even if the stiffness tends to 0, the maximum deformation in the structure should tend to R1. In a substep, arc length R1 is kept constant, as it indicates a maximum possible deformation in the structure, considering softening of the structure. As the substep 1, with load F1 converges, depending on the number of iterations required to converge the substep, R1 is scaled up or down. Up, if convergence was quick; down, if convergence is slow, indicating a large nonlinearity. The arc length in the next substep is estimated as R2 equals C multiplied by R1, where C is the scaling factor. If stiffness K2 of the structure at the end of the converged substep 1 is known, R2 is the maximum possible deformation of the structure, considering a scaling factor C. The maximum substep 2 size can be decided as F2 equal to arc length of the second substep R2. This indicates an infinitely stiff structure with deformation delta 2 equals 0. Thus, by carefully tracking the number of iterations required to converge the substep, and selecting an appropriate arc length scaling factor, it can be ensured that the solution is stable, and deformations do not exceed certain limits, regardless of stiffness change in the structure. Even for structures with stiffness close to 0, the solution can progress by incrementing the deformations by the arc length distance. This is the maximum possible deformation a structure can have with a given load application. The main advantage of the arc length method is it poses limits on the deformations in the structure, even when the stiffness of the structure becomes close to 0. Arc length method can be activated in ANSYS using the command snippet. As the arc length method decides the load increment, the automatic time stepping should be turned off. In order to activate arc length in ANSYS, add a command snippet in the structural analysis branch and give the following command: /solu arclen, on, 10, 0.001, where the first number 10 is the maximum permissible scaling factor for the arc length, and the second number, 0.001, is the smallest permissible scaling factor for the arc length. ANSYS selects the appropriate scaling factor between the specified limits to scale the arc length and solve the model. Note that the highest possible arc length scaling factor in ANSYS is 25. The smallest possible arc length scaling factor in ANSYS is 0.0001.